everybody who's joining the Trillium webinar on hydrogen solutions. Just a couple of housekeeping items. There will be time for questions at the end. You can type your questions at any time in the Q&A box on the bottom of the Zoom window. So please take the time to do that, and we will try to answer any and all questions as they come up. With that, I'll let you start off, Sebastian.
Thanks. So my name is Sebastian, and I'm joined today with my colleague Simon Braccio. We want to thank you for taking time to attend from your busy schedule. Today we will talk about hydrogen. Hydrogen is a new market area, which is very booming as it's part of energy transition. It will help for energy transition to reduce partially CO2 emission worldwide. As you know, many countries involved and have their own roadmap to reduce CO2 emission and to reach the net zero emission target by 2050. But challenges are multiple, and more particularity from the infrastructure that need to be built to supply hydrogen, especially for transportation. At the Trillium Group, we are engaged to support solutions to reduce climate warming. We believe in energy transition and wish to contribute thanks to a hydrogen solution and patent model we develop for that. As you know, maybe Trillium supplies safety valve for hydrogen service from decade, and we will take the opportunity to highlight that during this webinar. Let's review the agenda of the day. So basically, it will be split in 4 sessions. First, as usual, we will briefly present Trillium. Then I will let Simon present the market challenge where we will likely to find hydrogen or not. I will talk about solution Sarrazin developed to fit with a hydrogen application, and we will finish by the Q&A session. But again, feel free to ask your question as they come up. We will reply at the end. Remember to keep presentation in the full screen mode, if possible, to see data, table, and graph, just a recommendation. So my name is Sébastien Vermeulen. I hold a master's degree in fine element analysis and joined the pressure valve industry in 2009. I became familiar with the ASME code during 5 years in the engineering department before joining Trillium, its product team, and being focused on the Sarrazin pressure valve line.
Hi, my name's Simon Bradshaw. I look after engineering for Trillium, and as it says there, I've been in the pump and valve industry pretty much my entire career. It's a pretty boring resume, 4 decades worth. I've done a bunch of stuff with a bunch of different companies, and now having fun doing this with Trillium.
So let's start with an overview of Trillium Flow Technology brand portfolio. In blue, you have pump brand, in green, valve brand. So in pump, we have Begman, Flowway, Gabionetta, API valve, Turbomechanica Pompe, Rotojet, Gabionetta API pumps, Rotojet, Remco, and WSP. From a valve perspective, we have Atwood and Morrill isolation and check valve, auto torque actuator, Batley butterfly valve, Blackborough control valve and choke valve, Hopkinson parallel slide gate valve, Sarrazin and Sabine pressure valve. So as you can see, a very large portfolio of valve solution, tricentric triple offset butterfly valve that even if it is dedicated for nuclear, could address also hydrogen, as well as a red point valve, all leading name in this industry. So if Trillium doesn't renew the bell as a minimum, we expect some of this brand name renew the bell. In total, it's a 17 long-standing trusted brand, which are manufactured on 12 different manufacturing facilities and 4 service centers localized throughout the US, UK, France, Italy, Netherlands, South Korea, China, and India. by 2,000 employees globally. So Trillium Flow Technology heritage of innovation span 190 years. The corporation is not standing still, adding new products and services to make our customer processes more efficient and productive. A recent example of this includes the previously mentioned Redpoint valve product and offering, joining the Trillium family in 2020, expanding our product and service provision for valve. And in 2022, we were joined by Turbomecanica Pumpe, enhancing our expertise and offering in pumps for power, water plus oil and gas, as well as enhancing the Trillium Flow service portfolio. Just to have a core focus on the PRV solution, and just also to demonstrate we address hydrogen market for decade. Sarrazin got its first PO from Air Liquide, which proposed unique solution for air separation unit, ASU, and steam methane reforming in 1984. So it's a long partnership, and we supply already a solution for cryogenic or high pressure valve. So let's try to first understand hydrogen challenge. I hand over to Simon for that.
Yeah, so thanks, Sebastian. All right, so let's just kind of break down a little bit the background of hydrogen. I'm sure some of you already know this, but it's probably worth just getting a good grounding around it. Just to remind you again, if you have any questions as we go through this, please type them in the Q&A box at the bottom of the Zoom window. This webinar will also be available on the Trillium YouTube channel after a couple of days. So if you do feel you missed something, you can always go there to get it. All right, so hydrogen, as it says there, it's pretty much the oldest, most abundant element in the universe. Typically, it's bound up with something. Water, hydrocarbons, organic matter, et cetera, et cetera. You may have seen in the news, there's some excitement over some sources of, geological sources of pure hydrogen. Whether that plays out to be anything remains to be seen at the moment. Hydrogen is very energetic. 1 kilogram of hydrogen has 3 times as much energy as a kilogram of gasoline or petrol, depending which part of the world you're in. However, the flip side of that is it has a very low density. So the graphic at the bottom is essentially just visualizing the space that will be taken up by 1 kilogram of hydrogen again. So at atmospheric pressure, you have an enormous volume. If you were to convert that hydrogen into ammonia, you can essentially drop that almost by a factor of 10. If you compress that hydrogen instead to 700 bar, you can get it down fairly small, and then if you liquefy it, you can get it smaller still. All of those methods of shrinking the space have their benefits and drawbacks, and you require specific valves and design to do the job effectively. Next slide. All right, hydrogen types. I'm sure most of you already know this. We'll hit the highlights on this. The main one, of course, that's in the news, gets everybody talking about, is green hydrogen, mainly because the idea is it's going to help reduce the world's carbon footprint, or at least that's the intent. Again, a lot of the news tends to be around green hydrogen from water electrolysis. But as you can see on the graph there are other methods of doing it besides that, some of which are less developed than others. You also may have come across pink and yellow hydrogen, which just denotes the type of electricity that's used to create it. The one that most hydrogen today is produced from natural gas, which is gray hydrogen, which is done through steam reforming. That has a very large carbon footprint, as it says there, because essentially you're stripping the hydrogen away and dumping the carbon out into the atmosphere. There is the possibility to do blue hydrogen, which is steam reforming plus some form of carbon capture, which will reduce the carbon footprint somewhat at the cost of increased energy consumption and the like. Next slide. All right. The other thing you tend to see in the news is that hydrogen is going to be this massive Swiss Army knife that's going to do everything. It's going to do transportation, it's going to do this, it's going to do that. The reality is that in the long run, and this is the long run market is not necessarily what we're in right now, but in the long run, there are certain applications are going to win out for hydrogen or more likely to win out for hydrogen, and some are not, just because of the economics and the technical details around it. So there's a couple of ways to look at this. One of these is the so-called hydrogen ladder, which is from Liebrecht and Associates. You can see the credits at the bottom there. And essentially the way they look at it is there's applications at the top of the ladder where there is no real alternative to using hydrogen. And, for example, fertilizer production, which, there's something like 185 million tons of ammonia is produced every year from gray hydrogen for that purpose. So you can see those along the top. Those will absolutely require green hydrogen in the future. It's almost 100% certainty. Then as you go down the ladder, you have the applications that are, there are some alternatives to using hydrogen, and those are shown there. A lot of them are simply electrification. And you get down to things like at the bottom at the level G, things that whilst it's not the probability is not zero, it's very close to zero that things like domestic heating will use hydrogen. The technical aspects and the economics just don't make sense in the long run, and it's unlikely that will prevail. Okay, next slide. This is from a different grouping, Energy Transition Commission from 2021, so it's a little bit older. It kind of says much of the same thing, so they just put it in a different way. They have the confidence in the role of hydrogen on the x-axis and the readiness in terms of technical readiness, economic readiness on the vertical, the y-axis. And you can see there the size of the bubble is the size of market or potential that they've identified. Some like fertilizer, methanol production, refining are already there. They have a very high confidence that hydrogen will be required, and the readiness is already there. Those processes are well known and understood. Ones like power storage, steel, shipping, aviation, they're much less mature, and there will definitely be work that will be required to make those happen. And then finally, we have a graph on hydrogen production. So the reason for this is showing you the trajectory of different production routes in terms of cost. So the way to read this graph is there's a red line and a green line, and they represent the costs for producing green hydrogen, depending on the cost of electricity. So they have it for a favorable location and also for an average location. And the takeaway here is when you put that up against the cost of creating blue hydrogen, which, if you remember, is using natural gas for steam reformation plus some form of carbon capture. If you look at the trajectory around the end of this decade, even in an average country, it looks like it will probably be favorable. In other words, it'll be more or less cost neutral as to whether you do blue hydrogen or green hydrogen. And so that's the kind of end point that we in Trillium are kind of looking at, where green hydrogen really takes off. Okay. With that, I think I'm handing back to Sebastian.
So there are different kind of hydrogen application, as we understand now, from production to sample use, from also upstream to downstream, and obviously we will find different kind of application to serve this market. We won't cover all of them. Today we consider 39% is in the industry sector, 30% in transport, 26% in heating and power for building, 5% in power generation. So again, the idea is to show in this graphic the connection between the different application and the the product portfolio we can offer. If you look at the upstream, so typically, as mentioned by Simon, if we consider gray hydrogen, steam methane reforming, where we will deal with syngas or synthetic gas, where we will split hydrogen to carbon monoxide. It's a mix, so the gas is not purified yet, and you can find a mix of different kind of solution, from spring-loaded to a pilot-operated solution, either semi-nozzle or full nozzle type. Full nozzle being preferred to reduce the leakage rate. Another segment is a power. On that case, hydrogen being used as a fuel to convert water into steam. The valve won't see directly hydrogen. It will be a standard steam valve connect to a part of a hydrogen market, but not directly, indirectly. So obviously it's not the topic of the day, but it's just to highlight we can have we can propose solution to deal with a steam application connect on this market as well. Today we will be more focused on the hydrogen refueling station and this patented solution that has been developed especially for this market, so H2 star. We will review all together. It's a quite important step forward because in the H2 commercialization, we need to adopt infrastructure that meet regulation in terms of safety and reliability. So let's try to go more in depth on to understand what means safety and reliability and the concern that are all around hydrogen. So as mentioned by Simon earlier, hydrogen is odorless, colorless, but on top of that is very flammable. And the biggest concern is also, even if we talk about blue hydrogen or green hydrogen, by green it means, okay, potentially it doesn't have direct impact on the greenhouse gas emission, which is partially true, but also partially wrong. If hydrogen will help to reduce the carbon dioxide emission, it will also have indirect negative impact on the global warming, up to 5.8 times worse than CO2 emission. So how does that come, or how is it possible? The answer is not so easy to understand, but we will explain it. Once it is released directly into the atmosphere, hydrogen itself can interact with other gases and vapor in the air to produce powerful warming effect. As an example, hydrogen can extend the lifetime of atmospheric methane, so methane which is connected to LNG market indirectly, which is also an incredibly potent greenhouse gas, GHG gas, causing some 80 times more warming effect than an equivalent weight of CO2 over the first 20 years. So we understand it's quite important to reduce hydrogen emission, even if it is a green hydrogen. How to do it? Reduce leakage. Leakage are everywhere when you at upstream, but also during transportation and also during storage. If we consider the vessel that has been identified, the gas cylinder we talked just earlier, we can assume that we will use between 0.12 to 0.24% per day. It looks like nothing, but at the end, if you combine here if you consider the leakage on a complete year and the quantity of vessels that are supposed to be developed in the upcoming year, it will be significant. So this is where Trillium will operate. How? Dealing with a solution to reduce leakage and to make to develop a robust design. One of the key things, it's of course to deal with the high pressure. We already see it, up to 10,000 bar. Propose the right material, we will see this, but on top of that, reduce the leakage. there is a study that has been performed by the National Renewable Energy Laboratory, the NREL, about PLV reliability. The result is 45% of safety valve were within the spec. By spec, it means comply with what we can expect when you buy PRV, to be open at the right set pressure, to keep the right tightness, to release the capacity. That means 55% of PRV fail. If we go more in depth on this failure, the majority, 34%, fail due to the wrong set pressure tolerance. 5% fail to open or keep open. 16% have a leak rate issue above the spec. So it is really important to, even if safety valve we recognize doesn't have an impact on the operation, to improve your process when it's run properly, as soon as it fails, the complete process has to be put on hold. The process cannot run because it is part of the regulation to be protected by PRV. If the PRV is not activated or is not installed properly, you have to stop. This is part of the regulation. So we get in the third part. Let us now present the product and the test we put all around this new design. So as said earlier, this solution is especially developed for hydrogen refueling station. So it's only part of one single business. The first thing is, what about the service condition for hydrogen refueling station? What kind of pressure we can expect? We can see we have two kind of pressure, 550 bar and up to 1034 bar. The pressure is staggered. The main reason is H2 shall pass through compressor, then store on a compressed hydrogen storage tank before being supplied through a dispenser. It's part of the process. As of today, due to the low molecular weight, high diffusibility, we adopt spring-loaded valve due to its robust design. What about the application code? Behind that, we still comply with ASME requirement. So it means the set pressure tolerance will be plus or minus 3%. The blowdown will be at 7% as it is adjustable blowdown. The overpressure can be either 10, 16% if it is multiple valve scenario, which is obviously the case. Regulation about or all around hydrogen are quite new. Each country has its own regulation. If you go in China, they have a regulation, in Europe as well. We consider today a regulation that has been developed by the Institution Classified for Environmental Protection, the ICPE. And looking at that, it starts to have a structure that has been established for any hydrogen dispenser that has to operate at a pressure lower than 700 bar and whose total capacity should be below 120 grams per second. And it is clearly mentioned on that case, such kind of design should be adopted. The dispenser should be protected by safety device, like a thermal expansion valve like this. So in terms of solution, we perform some, so the issue on such kind of product is the cycling effect. When you reach high pressure and the valve is discharging, you have some pressure gradient. So we perform some cycling effect. It is also the true for dispenser. We have different kind of dispenser we have to consider. Type 4 is for the 700 bar. It's a composite liner. And the specificity of this design is we minimize the dead space to avoid hydrogen gas pockets, to reduce also the static fatigue. We take the opportunity to just do a brief parenthesis to talk about liquid hydrogen, even if today it's not considered for hydrogen refueling station. It could be a solution in the future. As we said earlier, you have a choice between provide high pressure or liquefied, the idea being to reduce the volume of hydrogen through dispenser to supply hydrogen on hydrogen car. So Again, liquid hydrogen is not very new. We provide through air separator unit in 2012, 2013, and we continue. But the design should be, we need to make some adjustments to adopt some specific design, adopting spacer. So using spacers, the idea is to protect the spring. Spring has its own material. If you cool down the spring, you increase the stiffness and you modify the set point. So that's the reason spring should be protected and spacer should be adapted. Also, we need to adopt a dry lubricant to avoid solidification in the valve stream. So it's part of consideration we adopt when we have to deal with liquid hydrogen or over any specific pure media. Very briefly, before handing over Simon, we will just go more in depth on this specific topic. If we talk about PRV, we have to consider different kind of material category. Some of them has to be considered our pressure containing part. This is the envelope, what avoid hydrogen to escape directly to atmosphere. So we talk about the body, the bonnet, and the cap. We also talk about the weighted part, the part that are continuously exposed to hydrogen. A valve is a normally closed device. It means it's not supposed to discharge continuously, and we have a limited number of components that are weighted part. This is true for the nozzle at inlet and the disc. These two parts are especially exposed to hydrogen attack, and we can have very quickly a material property degradation of the nozzle. The same laboratories, NRER, perform a study during a 10-year cycle count on such kind of material, and at the end, a nozzle has been damaged. So that's the reason we have to pay attention on material selection. Mainly 316L is preferred. We cannot adopt high-grade full tensile material, harder material, due to embrittlement issue. But I will let Simon develop this. But just before, I will also introduce some other product as a Trillium group we can propose for as a hydrogen solution to deal with hydrogen. You might be on mute, Simon.
Yeah, sorry guys. Okay, so just although this this webinar is primarily focused on hydrogen and safety valves, this is just to make the point that Trillium has historically provided many other types of valves into hydrogen service. This is, as Sebastian said, not a new thing for us. And I thought we'd throw a couple of those up there and then just talk about some of the specific, challenges with handling hydrogen as a gas or a liquid. So this one here was a Bladeborough parallel slide gate valve for hot hydrogen service, and up to say around 400 Fahrenheit, 200 degrees Celsius. We can supply these valves in a number of configurations and a number of different sizes. The key thing to kind of note is the sealing conditions, which Sebastian talked about earlier, because we don't want the hydrogen leaking out. That's a bad thing. I'm going to go to the next slide. And this one's for cryogenic service. These are generic cross sections, by the way, not specific, but they give you an idea. So again, fully qualified for hydrogen service, which is actually quite hard to do. There are some very specific things that are required in terms of validation of the materials to avoid degradation, cracking, that kind of thing. Again, very stringent sealing conditions required. And then if we want to talk about what do we actually need to do for design of hydrogen? Well, it's a pretty small molecule. That's the first issue. So it likes to diffuse through stuff. That's its kind of modus operandi. Hydrogen embrittlement is a thing. It primarily affects high strength steels. Actually, pipeline steels are one of the big concerns there. But there are there is the potential to negatively affect other materials depending on the variables that you see there, temperature, pressure, etc. So this embrittlement occurs at the molecular level. It will reduce the ductility, and over time you'll end up with cracks like you see there in the graphic below. That tends to be a bad thing because at some point that crack will grow and you'll get a rupture, essentially a sudden failure. And if it's not picked up by NDE, routine NDE, that would be a very bad situation. Next slide. The other thing is on the non-metallic parts of the valve. Those are also challenging. Again, hydrogen being a small molecule, it likes to diffuse into things. CO2 actually has a similar propensity to do that. And hydrogen blistering is a common issue experienced with polymers put into these kinds of services. You can see there an example of an O-ring that originally was an O-ring and now isn't an O-ring because it's got multiple blisters that have occurred during pressure cycling. Now, obviously, once it fails to do its job in sealing, you now have potentially much higher levels of emissions, which is something that we don't want. There are polymers that are better suited to hydrogen. PTFE is less sensitive to friction and to swelling on hydrogen compared to EPDM or nitrile. There are caveats to using that, however, and the design needs to be adapted appropriately for it to work and achieve, again, the tightness that we're looking for. And with that, I'll hand you back to Sebastian.
One more thing we can add regarding this specific H2 star solution is the connection. Connection is, we also have to pay attention to connection because it can be source of leakage as well. So we adopt cone thread solution as first because it's offer premium performance to handle high pressure. Even if, as we can see, there is some alternative that offer better performance in terms of tightness and seismic. But first, we have to pay attention of this specific high pressure. So as I explained, we have to look at a compromise here, and the best compromise was to select a cone and thread solution. So it's good to have a dedicated product for that, but it's also better to test it properly, as we discussed earlier. Some valve might have to fail due to a wrong setting or a leakage issue. So it's part of our job, our daily job, to deal with that and to test the valve properly. As main manufacturer, we have to meet some requirement, and we will take the opportunity to explain a part of our process to in general, and more specifically to deal with hydrogen services. So it's different step. Here we have to separate safety function and performance. In terms of safety function, regardless the product category, it can be either spring or pilot. A pressure valve is first a self-actuated product that has to be able to only meet two safety criteria: to be open at set pressure and to relieve the capacity. When we set open at set pressure, it means not only one time, but it has to be demonstrated at least 3 times. So that's the reason why we measure the valve set pressure. We make the valve pop 3 times. We make the pressure increase slightly. We need to respect a certain pressure gradient, and we make the valve open 3 times. Each time we check the value, and so the value is when you have this pressure drop from 150, 500 to 500. And we check the 3 value that has been measured are within the set pressure tolerance that has been defined as ASME section 13. It is between plus and minus 3%. If you succeed, you can go to the next step. For hydrogen, we not only perform the test on air, but we can also perform the test in helium. First, because helium is a thin molecule as well, which is quite close to hydrogen, so we reproduce the current scenario. We also use helium to measure to perform leak tightness. Helium can be either used in ambient temperature, but we can also use it to simulate cryogenic condition. So in Saint-Razin, we are also equipped with a cryogenic test bench. It's a boil-off, so it means the process itself is cooled down to reproduce the actual process condition. With the difference, we here use nitrogen, so the temperature is not so low. It's not a minus. For hydrogen, the boiling point is minus 253. We reach minus 196 degrees Celsius. It's part of the challenge to be able to test the valve on the value which are lower than that, using helium, for example, with the boiling point is minus 269 degrees Celsius. But we have to use a specific laboratory testing on that case. But on that case, for the moment, in-house, what we can do is we use nitrogen, liquid nitrogen, to push on the helium gas, which is localized on the top side of the vessel, to make the valve open in helium and to perform also helium testing for leakage. So leak tight test. So leak tight is the second part of the process. If you succeed to set pressure test. In this video, as you can see, we have also some valve, pilot operated valves, not only thermal expansion, that has been qualified for a cryogenic application as well, which is largely used for FLNG industry, but it's a separate topic. So the next step is to measure the seat tightness. So by seat tightness, it's on that case, we follow API standard 527. It's a guideline. By guideline, it means we can supersede API standard 527. It's if we follow the process explains how to perform the test. So for example, on that case, we talk about the valve with a set point is 550. We have as a minimum to perform the test at 90% of the set pressure, this part of this guideline. But on that case, we raise the bar, we test the valve up to 95, even up to 535 bar, as you can see on this video. The valve is tight at 535, so it's higher than 95%. 95% is the warranty, what we warranty now. So we stabilize the pressure. We make the pressure increase from 0 to 555, 35, sorry. We stabilize the pressure and we put a blind flange at the outlet, and we make sure we have zero bubble. This is part of the API requirement when we have to use a soft seat. Zero bubble is acceptable for a minimum duration. On that case, it's a 1 minute. And if again, this is part of the process to comply with API requirement for seat tightness at inlet. We also perform something similar at outlet, measuring the potential leak rate through the pressure containing part. By pressure containing part, it means including the body bonnet bolting connection, the body nozzle connection, body adjusting screw connection. Also, we check the body cap connection on top side and the valve inlet outlet as well. For that, we use a specific device, a sniffer, because the particles are so thin, we have to use it. So Tritium criteria are even more stringent or basic customer requirement, which is about 10-4 Pascal cubic meter per second. That represents 1 bubble per minute, if we have to compare. Again, The last part, but not the less important, is we are dealing with pure gas, pure process. It's something Trillium used to deal with, not only for hydrogen, but also for oxygen service application that are more or less the same. When we have to deal with new markets, we won't reinvent the wheel. It's not only true for Trillium, but it is regarding the applicable standard. One of them, which is recognized, is the CGA 4.1 for it is a standard that it is an internationally harmonized publication, and it is referenced by the National Fire Protection Association, the NFPA. This describes the cleaning method and requirement for equipment used in the production, storage, distribution, and use of liquid and gaseous oxygen to reduce the risk of fire, explosion, or promotion of combustion. So it is something which is clearly recognized. And we follow this method to deal with hydrogen. Part of the process is to have a new area to handle acid cleaning and to separate as well carbon steel and stainless steel material to avoid impurity. Even if we said for hydrogen, we only deal with stainless steel valve, it can happen. We have to handle different kind of purchase order, different kind of application. And on that case, we don't mix both. That's the most important. So we have cleaning at any stage. Acid cleaning is part of them. We also have a completely new white room where we pay attention on all the devices that are installed. It means the test bench are degrees, all the machine and tools that are used are completely degrees, and this cleaning room has a restricted access. Employee who get in there has also specific equipment, specific clothes. So parts are clean before assembly. Then we also use specific lubricant during assembly. And after assembly, after testing, the complete valve is put either on the, we can also consider double seal welded pockets with intermediate desiccant if required to make sure the valve keep a perfect tightness from shipment to a customer site. So it's a method we put in place with a dedicated employee that has been trained to follow this process. And to support that, we also use a specific non-destructive examination. So wipe white is the first level, but we also use a white and black light inspection on this dedicated area using a wood lamp. We now arrive to the Q&A session. So just before, as a summary, we just want to remind you in a brief some headline regarding the customer concern. So here, the main challenge is we have to deal for the moment with gas hydrogen at quite high pressure, where we have to use a specific connection, specific process to clean to clean the valves to avoid ignition or to reduce the flammable risk. We also have to, because it's a pure hydrogen, we also have to reduce any risk of leakage, to reduce greenhouse gas emission indirectly, even if it is a green hydrogen. And because we talk about hydrogen refueling stations, so it's automotive industry, we need to make it run 24 hours by 7. So maintenance is very important to have solution to quickly replace or offer a product which is premium at a reasonable price. To meet this customer requirement, we develop specific feature, a block, a small thermal expansion valve, a robust design with a reduced dead space, full stainless steel, 316L design, that will be tested and adjust by a qualified operator. What's the consequence? What's the total potential value of this combination between customer needs and feature we put in place? First, we meet the market demands and the associated local regulation, whether in France or overseas. Depending on the territory and the policy that has been put in place, the fine, as you can see, can be potentially crazy expensive. The gap is significant, but it also depends on the tolerance the local regulation put in place. And as I said earlier, keep in mind, even if PRV industry, it's true, it doesn't have any impact on your process. This said, it's partially wrong because we meet, we guarantee a very high tightness, and the pressure is the money maker. The higher pressure, the better performance you can expect. And to reach 95% of tightness, 95% of the set pressure has a tightness, as an operating pressure as well, that will have a positive impact on the total process. We said when it is done, and it is a challenge for a spring-loaded valve. But when it is done, as long as the PRV work, it doesn't have any impact on your process. The drawback is if we have the PRV that stay in open position or start to leak, then you have to stop the complete process. So that's part of the issue, and that has a significant drawback, that could have a significant drawback in case you have a maintenance outage from 10,000 to 40 key per day. So having this robust design will help you to solve that. And well, again, we won't repeat, but spring-loaded is a robust design that offer reliability, so that doesn't have any price for that. So we arrive at the end of this session. Don't hesitate to visit our virtual trade show, or as Simon said earlier, to scan the QR code to get a quick access to our YouTube page, where we have not 1,000, but close to 100 webinar session now relative to safety valve sizing or fast track valve solution for FPSO application, some much more, quite interesting, not much more, but quite interesting topic as well. We could that could catch your attention. Thanks.
All right, thanks, Sebastian. So just again, a reminder, this is kind of your last chance. If you have a question after listening to all that, please put it in the Q&A box. That said, we have a few questions here. So I'll kind of start at the top. So the first question is, for safety valves, do you recommend a rupture disc to avoid leakages? Thank you. Do you want to take that one?
Yes, of course, it's better. So to just to give you a brief overview, safety valve can be first combined with rupture disc. No issue about that. A rupture disc, it's a non-reclosing device. It means when the disc bursts, but you need to replace it. So indirectly, you increase your maintenance cost because you have to pay for rupture disc replacement. So it's not a good idea if you want to consider a very high operating pressure, because the risk to have the rupture disc burst is quite high. And if you have to replace the rupture disc again and again, it doesn't help. Now, we said rupture disc is on-off. If it's tight, it's 100% tight, no leakage. But it can only be adopted if your operating pressure is quite far. Otherwise, you have to disassemble, repair the disc. So it doesn't make really sense. So it can be, but it needs to be select with cautious. And most of the time, it is select when you don't have any pressure peak and you have an operating pressure which is far from your opening. Most of the time when rupture disc open, immediately the valve open just after. The only difference is you have maintenance on a rupture disc. It is a solution which is mainly used on the pharmaceutical industry, where finally you operate at the lowest pressure. For a rupture disc operating at 10,000 bar, it will have it can be considered, but it's not happened yet. And again, well, on this kind of solution, we offer premium performance in terms of tightness. Another drawback you have to consider for rupture disc is due to the fact rupture disc can potentially not be fully open, we have to oversize the safety valve to consider a 10% derivative coefficient factor. It means you will also indirectly increase the volume, so the potential hydrogen gas retention. So it's something we have to consider twice before adopting a rupture disk. For the moment, it's not the solution we have or discussion we have with our customer.
Okay, thanks, Sebastian. So the next question relates to, I was checking as you were talking, it relates to slide 18, where you talked about the height, the H2 star. And the question is, on one of the slides, slide 18, it had an overpressure of 10% or 0.2 bar.
16.
Yeah, sorry, get that one. No, yeah, the overpressure 10% or 0.2 bar is written on there. And the question is which one to use. I guess is what the questioner is looking for.
Okay. It's not part of a product specification. It's part of the standard, the code we have to follow. So 0.2 bar is when you have to consider a low pressure. But as we highlight during this webinar, it's for high pressure, 550 bar, 1000 bar. So we will consider 10%, whichever is higher. So it's 10% that has to be considered. And we also demonstrate, it's a pop action valve at the end. And 10% is again the minimum which is required by ASME to move from with the valve start to open, and bam, it reaches its open position. It's open position. But to make this transition, we need to generate 10% overpressure. Some customer, and it is the strategy, we recognize it's a strategy, ask to have a lower overpressure, potentially to increase the operating. It's not the right approach. It's strictly forbidden in any case to have a set pressure higher than the design pressure when we have single valve scenario. So if the design is if the design pressure is limited at 10,000 bar, the set pressure cannot be higher than 10,000 bar. Now, if the question behind that is to demonstrate the valve can be fully open at 5%, it is forbidden as per ASME code to address the European regulation, the Pressure Equipment Directive. We can perform some tests and demonstrate the valve is fully open at 5% overpressure. It is authorized in Europe, forbidden in US. So as I explained, depending on the territory, the end user market segment, what kind of temp is expected on the PRV, it has to be considered case by case.
All right, thanks, Sebastian. So next question we have is, the questioner says, I've seen that there are many different government and industry initiatives for hydrogen. That's true. How can Trillium help me identify the appropriate type of valve to specify for my application? So I think I'll take that one and just talk to it briefly so we can get to the last question we have here.
Okay.
So as you saw, there are a number of, and Sebastian talked to it, there are a number of evolving codes as the use of hydrogen evolves, and we're looking at different applications and different methods of storage, transportation, manufacture of hydrogen, etc. So just to be clear, Trillium does not make commodity valves. That's not what where we add value. Where we add value is the examples that Sebastian showed and I showed, where the customer comes to us and says, okay, here's my process, here's what I need to do. What do I need to be considering here, from a safety aspect, from a code aspect, etc., from a design and reliability aspect. And we'll happily work with them to develop and specify what that would be, considering all of the emerging specifications and codes that we do monitor very, very closely. And that's the value that you're getting with working with us on this, whatever the application would be. And I've no doubt there will be new applications and new requirements that will emerge in the future as we go through this rather interesting period of energy transition. So hopefully that answered that question. The last one that I have here is a question. It's a nice short one. It says, do you supply spares and service for the H2 star valve, the one you were talking about?
Yes, good question. We can, of course. Now, as I explained earlier, we address a specific market, which is automotive industry, hydrogen core, and it needs to have a quick turnaround. And because we have to deal with some specific process, as soon as we apply a specific stamp, we demonstrate as a manufacturer we have all capability to adjust the valve setting and to perform the associated test about that. It can take time. It can take time to identify the root cause of failure if we have, or to supply some spares. And we are talking about a small valve where we identify the market, the pressure, the pressure class, the material. So we put in place a dedicated stock to address specifically this market and to ensure a quick turnaround. And it's a good deal at the end to work hand on hand and in right partnership with customer and to propose a complete valve replacement to address this specific market. So we can do both, but at the end, the deal is to offer also a dedicated inventory stock to have a quick shift in case if it is needed on this. But that's the right answer we propose.
Yeah, and I mean, I think it's worth noting these are valves for safety critical applications typically, and as Sebastian laid out, there are a number of very specific processes that are used in the testing and cleaning, packaging of the valves, and sending out a bunch of spare parts. You have we essentially have no assurance of how those are going to be put together. So that's something to think about. We're talking about very, stuff you should be controlling if you want to be successful. All right, so we've reached the end of the questions. Thank you all for your attendance. I appreciate your time out of your day to do so. Hopefully you found it useful. You can rewatch this if you've missed part of it at the Trillium YouTube website, where it should be available within a couple of days. So with that, we'll close the webinar, and thank you.